Welcome back after the break. So now to our next talk, coherent optical transceivers. What's the status? What's the outlook? We have here on the stage Thomas and Gerhard from Flex Optics. Gerhard is head of business product development, and Thomas as the intellectual brain of all the company. Thomas is with DENOG since DENOG1, so very long. So I'm very excited that he's still here, and every DENOG again here. We will hear about the 400G pluggables, about OIForum interop tests, about Nokia insights. So the stage is yours. Thank you.
Perfect. Hi, my name is thomas.weible, CTO of Flex Optics, and I'm really proud today being here. So I brought a topic together with Gerhard, coherent optical transceivers. Gerhard will introduce himself later on as well. And we also try to play a small game later on. And, but before I'm going to start dig into the topic of coherent transceivers, I want to do a small recap from the last DENOG15. So I took a raw copy from Florian Hiebler's presentation from Arista last time, and he made a really great presentation about 400 gig ZR Plus, where they did real-world examples of links in the US up to a couple of 100 kilometers with coherent transceivers. And he summarized it quite well at the end. And I was quite curious when I saw this final conclusion somehow. So when I founded Flex Optics 15 years ago, it was always about unsupported transceivers, the battle of optics. Transceivers were not supported in the gear. And now 15 years later, and I never expected that, we are talking about unsupported platforms. So the transceiver is not the issue any longer, it's more the platform. This was quite interesting to see. The reason why Florian mentioned that is the power consumption, and I will also later on talk a little bit about this. So I will hand over to Gerhard. He will do some theory part, and while he is talking, I will prepare something. Thank you.
All right, thank you very much, Thomas, and good afternoon, welcome. I'm Gerhard Stein, Head of Product Development, and I will talk a little bit about coherent transceiver, and it's a very, very basic theory. And a good point where to start with that is comparing it to the classical, I call them like that, transceivers, called as direct detection transceivers, and see the difference. So one challenge we have here is whenever we want to transmit a binary signal, like that one, where we have, let me move the cursor a bit, these waves basically are being converted because it becomes an analog signal and it is being transferred. Our problem is whenever we increase the frequency and we are squeezing the signal, basically it gets harder from the photo detection side to really detect the signal. You have to set different thresholds. That is one challenge. The second thing is we are just looking at a given frequency and amplitude. So we are really missing an opportunity because light has way more properties. And for what I want to begin with is an interesting property you see on your notebook when you buy some privacy shield. I think some of you have that. Polarization effect. If I move this paper, as you can see, the light is being blocked, and that is one of the effects a coherent transceiver can benefit from. And the second property is phase, because you can build up a laser that gets into your signal with a different phase, and that combination is quite interesting. Let me show you a video about that. I hope you can see it. Yeah, you can see it perfectly. That's a dream. So when we're talking about polarization, imagine that is a section of your optical fiber. Yeah? Here we have the Z direction or time, because you're transferring signal over the time. And we were talking about a sine signal, which you do not see here because you also have phase. I get a later slide on that. And what we are transferring here is a 16 quadrature amplitude modulation signal. I get to that in a moment. Let's talk first about polarization. And the special effect we have here, since it's two-dimensional, because you have a cross-section of your fiber, what basically happens is, when we play this guy, you are looking from the side on your fiber, imagine that, and now we are starting to rotate it. It's a little bit slow. Here we go. So you can see the Y plane, you can see the X plane. Now I am looking from top on it. And if you look closely, the signal is quite different. So what in reality happens here, you have skewness, you have a strange sinus wave, a combination of sinus waves with different phases. But what really happens with the polarization is you have a three-dimensional signal. And that's quite an interesting fact. So this messy signal you see here, where 160 bytes of random data transferred, need to be composed by a coherent transceiver, which leads to, of course, more complex subassembly. Having talked about polarization, let's get back to one polarized plane, which is, in our case, our X plane. The same is happening on the Y plane. We don't need to talk about it. I just want to show that really it's three-dimensional. And what can we do with phase and amplitude? And the interesting part of this is, per carrier, you can pack more bits. That is what basically is happening. And in order to demonstrate that with the audience, we are going to simulate a coherent transceiver. You as an audience are the transceiver. And please lift your hand. Who has a card? All right, cool. And we are playing a coherent transceiver here. So what we are going to do is, I, as a DSP, digital signal processor, want to process a signal. I want to send it over the fiber. So we start with 1, 1, 1, 1, also 4 times 1. And please raise your hand, those who think that have the signal assigned. Who has it? Who is in this plane? Okay, I'm counting 1. Just 1. Okay. So basically, it's this guy here. We have an angle of 45 degrees, an amplitude of 33%. All right, good. Let's continue with the next one. We are just transferring 12 bits because we don't want to be too long here, right? We still have a social event going on. So next signal, 0101. Who has it? Who has a card for that? The proper card? Yeah. Okay. Okay. So basically, amplitude of 33% and an angle of minus 135 degrees. I'm counting. How many? Okay. Just 1? Okay. All right. And last but not least, 0011. Who has that? It would be, where would be this signal? We have it like, where do we have it? Like here? Which is 100 and something, more than 135, and 75%. 160, yeah. Okay. Well, with that we can calculate in bit error rate. I counted like one that was not correct. So let's say 1 divided by 12. If I'm making mistakes, that's another bit error rate. We have a bit error rate of 8%, which is a great transmitter, I'd say. Now, they can do better, but still, very good. And thank you very much. Great audience. All right. But there are more ways to measure signal quality, and if we get our bits transferred as we need. The signal-to-noise ratio is a unit that is commonly used in fiber, and with the Nokia switch, we are going to show some logs. We have the SNR, which is electrical part, because you always have an electrical and an optical part. And yeah, that is what basically it means. And the signal-to-noise ratio is basically the distance of your EDO signal you want, and the noise as the mean value here, and the difference of it, which means, in consequence, the higher the signal is, the fewer problems you have with distortion. If you have more noise here, it's less tolerant to that. And this signal-to-noise ratio obviously also influences the bit error ratio. So when we get back to our 16-QAM diagram, hoppla, this was too fast. If we have an SNR of 30 dB, basically we are hitting the sweet spots where we want them, but the more we decrease the signal, the more it becomes scattered. As you can see, with 5 dB, it's not so good anymore. So we have bit error rate, we have SNR, and last but not least, another interesting unit is error vector, basically error vector magnitude. A lot of complex stuff, we can't talk about it, but really it's a vector. A vector has a length and an orientation, and what really matters to us here, and hopefully also for the SROS when they start supporting it, is the constellation point is the ideal point where we want to see our signal, and the place where you're standing is a deviation where you should not be. And basically what you want to do is to reduce this error vector magnitude to get it to 0. But if you want to look at more details, of course you can do that. For example, you have an IQ phase error, which could mean that your local oscillator is a little bit weird and not giving the right phase, like you have a deviation there. Or maybe your signal is too weak and it could lead to an IQ magnitude error. That's one example. If you're more the mathematical guy, you could say, okay, in my complex plane, the quadrature part, which is the imaginary part, and the in-phase part, which is the real part, you can see it's a deviation. It really depends what you want to look at, but I think we all agree that we want to reduce this error vector magnitude. Bring it to 0, bring it down to 0. And yeah, thank you very much. I'm handing over to Thomas. And we will see the practical part of all that.
Yeah, so we got now the theoretical part about the coherent detection, basically. And so what we did is we took a coherent transceiver, and together with Daniel Melzer from DKIX, we basically plugged it into his Nokia gear and run on an SROS a pretty simple command, the show port command. And that's all what we did. And then we looked in detail what is the show port command giving us as a feedback on an active link, and how we can troubleshoot and analyze that link. And these are basically 3 sections. So the first one is the typical CLI, which you see there, and I marked the green parts, which basically identify also our coherent transceiver. It is a fully tunable one, and on the min and max frequency set, which is shown here in megahertz, and typically people use terahertz there, you see the beginning and the end of the tunable. So it's 191.3 or .30 terahertz, which is channel 13, up to channel 61, which is the 196.10 terahertz. We are currently, we don't make a game now, but we are currently tuned to channel 23, as you can see, and we got a couple of grids supported. The typical well-known one is the 100 gigahertz grid, which I'm pretty sure everyone here who operates a DWDM network runs already. There is also the 50 gigahertz grid, and you see slices like 75, 25, and down to 6.25 gigahertz. So we can really slice it down depending on the application you're running, because when you, from the last presentation last year, you know, a 400 gig coherent transceiver is not only 400 gig, you can also do less, like 100 gig. Worth to mention, and I don't want to spend too much time on that, digital diagnostic should be known by now, and hopefully everyone has implemented in his operating system, and also you guys use it in your daily work to get the data out of it. On a coherent transceiver, the digital diagnostic is straightforward, and I think it's worth to mention to capture and to look at the temperature, especially of the module, because this was also a conclusion of the unsupported platforms. When they draw and they take a lot of power, and when they draw too much power out of that port, the temperature will go up, because the only thing what we have in an optical transceiver is we feed power in there, and we get pretty much heat out there. A little bit light for sure, but not much, and the majority of the energy is into the heat and temperature then. So you better watch about the temperature there. And now we come to the coherent optical parameters, and this is like the overview you get from a Nokia gear, what it shows you on an active link. So keep in mind this link is roughly 15 kilometers long, and it's operational with 400 gigabit. So we go now step by step through. The first thing is that the RX channel, and this is not the TX one, so the RX channel can be tuned, and it's required to be tuned, because you need to set the local oscillator, which is on the receiver side, needs to lock on that frequency what he's receiving, and that's really critical and needed, because otherwise your link won't come up. So the TX side on the other side is transmitting on channel 23, and our receiver also needs to know where is my center frequency. There is no sweeping, so you can't go through the band. You have to do this manually, but this is important. Depending on the implementation of the operating system, it's going to be automatically, when you tune the frequency on the TX side to channel 23, for example, it assumes that it also needs to receive the signal on 23, but on the Nokia gear you can precisely set it on the RX1. And that's a major change compared with the well-known 10 gig tunable modules, which I assume some of you operate. There you didn't have to take care about a receiver. Now you have to take care about a receiver. Next one is chromatic dispersion. We have a really, really powerful DSP in there, and he can measure the chromatic dispersion. Chromatic dispersion is the time difference when your signal traverse on the fiber, and it's going to be delayed or accelerated on the fiber while it's traversing. Some of you might notice there was an issue when you, back in those days, running 10 gigabit with CWDM. Chromatic dispersion was always a serious concern when we went up to, or lower to 1290 nanometer, for example, or even up to the 1610 window. So chromatic dispersion was a serious issue there. The great thing about coherent transceivers is they first can detect it, and secondly, they have a broad range how they compensate it. So our link here has a sweeping range from plus 2000 picoseconds per nanometer up to, or down to minus 25,000, which is a broad range. And the actual link was only running at 220 picoseconds per nanometer. And when you know the characteristics of your fiber, which is typically G.652 fiber, roughly 10 till 15 picoseconds per nanometer by kilometer, you do your math, you come to the 15 kilometer link. There is a little bit of an offset in there, so we did also a test with a back-to-back link in the lab with 2 meter patch cord, and we got there 80 picoseconds per nanometer, so you have to offset that. We couldn't figure out why there is that offset, but when you do the offset of 80 picoseconds per nanometer, you come to those roughly 150 picoseconds. Right. Then another dispersion thing beside the chromatic dispersion you need to bear in mind now, as we are, what Gerhard mentioned about, we have a 16 QAM signal, which is dual polarization. This was the thingy with the two filters. So we have two axes, X and Y axis, so our signal is 9 degrees shifted. There can also be a propagation delay, how fast the two signals are going through my fiber, and that's a different group delay, or how it is measured. And it's also a characteristic of your fiber, so look at the data sheet of the fiber you're running, and typically the transceivers can compensate up to 10 picoseconds the delay of the two axes. Now, this was a picture I took beginning last Friday, actually, in the morning. I went for a walk outside around our headquarters, and I saw this nice, those nice swarm of migrant birds traveling towards the south. And why is this working? Because typically they have a pilot in front of them flying towards the direction, and when he is tired, he goes back, and the next one is the pilot. So even in our signal, we need a pilot. And we call this the pilot sequence. So on our 16 QAM signal, we add 4, or we use basically 4 out of those 16 constellation points as a pilot signal. And the great thing with those pilot points is we are able to detect phase shift, which can, for example, occur when there is a lightning strike on your fiber, that the phase can shift. And with those pilot sequences, because they are always in the same order on maximum amplitude, we can identify a phase shift. In the Nokia gear, there is called this CPR window size, that's the carrier phase recovery. So how does this work? You typically sample a certain amount of symbols until you change the phase, or if you're going to correct it. So here it's set to 32 symbols. And the lower the number is, the more noise you get on your link. But on the other side, when the number is getting bigger and bigger, it's taking a little bit longer to correct an error. So you also need to find the right spot for the CPR or carrier phase symbol right there. And then the final one was OSNR and Q margin. Some words about OSNR. Gerhard mentioned it, it's the ratio between our actually signal and the noise. So we want maximum distance there, and that's all related to the data sheet and the specs of your transceiver. So our link was running at 34 dB OSNR, which was quite good. There's a lot of margin between there. And then Nokia somehow, I don't know why, they introduced this Q margin, RX Q margin. And it took us a while to figure out, hey, what do they mean with RxQ margin? And then the rest of the industry calls this the Q factor, and then it made totally sense. So the Q factor is basically a metric to identify how much space our FAC is still having to correct errors, or is still able to correct errors. So in our case, the pre-FAC, that's before we enter the FAC, is at roughly -3, and we still have a margin of 2.4 dB for the FAC to still operate properly. On a back-to-back link, for example, we had a RxQ margin of roughly 4 dB, and the pre-FAC value was at roughly -4. So it was slightly better, and therefore the RxQ margin was higher, and our FAC was still capable to correct all the errors, to have an error-free transmission, because after the FAC, we don't want to have a high bit error rate. And the final part is, which is related, and this makes it a little bit weird, is about the compatibility. Also Florian mentioned in his talk, there are different, I don't want to call this standardizations, these are more multi-source agreements. So in the past, in 10 gig and 40 gig, there was mainly the MSA group, together with the IEEE defining Ethernet, and now there is OIF, the Optical Internet Forum. I really looked it up. They called themselves Optical Internet Forum, and now the newer one, the OpenZR Plus MSA. And interestingly, here what we saw is on this well-known application mode table. So these are all the application modes that a typical coherent transceiver can support. Now, you really need to look up what does your transceiver support and also what does your gear support, because all the white spots you see there on the Nokia config Spalten, sorry, which are still white spots, they are not supported from the operating system. So like a 2x200 gig operation is not supported currently or implemented. Even worse, or what made us curious, was the fact physically and also from the configuration part, the transceiver is configured only optical compliance to OIF, so amplified or unamplified. But we were able to set a compatibility mode, OpenZR, which actually doesn't match. You will see this on the next slide. There was no check at all. It enabled us the link, it was working, but actually it's wrong. And that's what I want to refer to, is when you look in those, there are a lot of tables now. This is a public document, an MSA document, which refers all to the different application codes which are defined. So it starts with 10 gig, and even 1 gig was defined there in the past. Now we have there 400 gig and the 800 gig and everything else beyond. We see here 400 gig G-base ZR, which is an IEEE, which everyone typically relates in his network with, because we're talking about IEEE Ethernet. Now, looking at the application codes for the OIF, they get their own, and OpenZR Plus get also their own, which is totally fine. But when you look at the specs behind that, the IEEE one, the 400 G-base ZR, has the same technical specifications like the OIF one. So it's a good question. How would a link work when on the right side is configured to OIF, for example, 400ZR DWDM amplified, and on the left side you configure it to 400G base ZR? I couldn't figure out the answer yet, but this is still an open question because the application rate is the same, 478.75 gigabits. We have one lane, and the signaling rate is at roughly 60 gigabaud. And for sure the same modulation. You might wonder why we have that high application rate. Typically Ethernet is running at 425 gigabit when you run straight 400 gigabit Ethernet. Those plus 10% roughly, this is overhead. Overhead for our FAC for sure, that the FAC can operate and correct errors, and for the pilot sequence, that we still can get the phase shift out of our modulated signal. Right. Outlook, where are we going to, and what is going to be on the technology side kind of doable? For sure, everyone knows the terms that we want to have 800 gig and 1.6 tera and even beyond, so we double it and 3.2 terabit. But how can we achieve it? So you have heard now quite some information about coherent detection, which was newly introduced for 400 gigabit. Before that, we had direct detection and PAM4 as modulation. Now, if we want to increase the data rate to another level, for sure, we can add more lanes on a transceiver instead of 4 having 8 lanes. So then we are at 800 gigabit, or we can change the modulation. So the current typical 400 gig transceivers running at PAM4, which are not coherent transceivers. And then if you, for example, want to go up to 1.6 terabit, you basically just throw PAM 16 QAM coherent or DP 16 QAM coherent on it, and you basically quadruple the data rate, and you come up to 1.6 terabit. The interesting part is then down there on the line rate. This is 50 gigabaud running on the lanes on the electrical side, but also there was development done in the last years to increase the bandwidth of an electrical lane towards 100 gigabaud and even 200 gigabaud, which is requiring totally different substrate. It's really high frequency getting there. So that's basically the triangle, or not even triangle, the constellation where we are, how we can achieve 800 gig, 1.6, and even beyond that. So we will see there quite a lot of movement, and it's not a single solution, I'm pretty sure. Coming back to the coherent part, there's also interesting things possible now. So when you think about this coherent modulated signal now, which has a lot of information in there, and on the left side you see this point-to-point link where we typically talk about is a 1 or 200 or 400 gig peer-to-peer link. You can split it up now. So you can do a breakout mode on the optical level, so you don't need a breakout cable. So you do the breakout on the optical level, called the DSZM. This is mainly driven by Infinera. They push it quite hard. They also founded a forum called the OpenZR forum. Get it out there, and with that DSZM, which is called a digital subcarrier multiplexing, you can slice down those 400 gigabit down to 16 times 25 gigabit basically, and that's how your spectrum will look like then afterwards. So what you see here is a breakout mode on a uplink with 2 times 100 gigabit, and for sure on the downstream we can do the 400 gig, for example. You could also do 4 times 100 gig or variations. One time you can give a subscriber 1 time 25 gigabit, the other one is getting 75 gigabit, so it's quite flexible. And these are some findings they made out of also GPON technology, where you can also give different subscribers bandwidth. And now we do this on an optical level. I think this is at the beginning, I would call it. And let's see if some others are also pushing it out. But it makes the applications very, very flexible and easy to scale up. Yeah, this brings us to the end of the talk. If there are questions, we are still in time. That's perfect. Thank you very much for listening. There's one question.
Test? Okay, now we have a microphone. Thank you. When a coherent link initially comes up, how does the receiver sync to what the 0 point for phase and for phase is? Because as far as I understand, there's a reference signal running on the receiver end.
Yes.
But how does the receiver know if it is running in phase with the transmitter?
Okay. So on the receiver side, there's running an optical local oscillator, which is actually on the same frequency like the carrier. And then you can deduct with the DSP, you can deduct the signal and just get your NUT signal out of it, which has a really lower bandwidth then. That's how you get it out.
Yes, but like if there are like 2 signals, how do they know that their 0 degree phase point is at the same point in time?
Do you mean because of polarization?
No, but
okay.
The phase is like when we are running over phase, it's basically like shifting when the signal is running through its 0 point, right?
Yeah. Let's do it like this. We can look later on the block diagram, which components in front of it also take care about the phase shift. How does this sound?
Yes, thank you.
Welcome.
Thank you. Are there any other questions in the audience? I don't see any, and I don't see any here in the chat, right? So then thank you, Thomas and Gerhard.
Thank you, Tim.
Thank you.